So dear chemists, now what we are going to discuss is the first order reaction. We're going to look at the formula for finding the half-life and also the formula for generally determining the rate of the equation, the rate of the reaction for first order reactions. And a recap on zero order. Zero order, we said T a half is equal to the initial concentration out of 2 divided by K. And K has units of moles per decimeter cubed per second. So let's go to how we get this expression for first order reaction. And now we are going to consider rate, first of all, for first order is equal to K into A, okay? Then we also know that the reduction of the reactant A with respect to time is also going to give us rate. So if I equate these two, that means negative dA dt will equal to K A. So here you can see that it's first order because the power of the concentration of A is 1. So let's proceed. We are going to correct like terms and then or separate variables. So let's separate the variables and we have negative dA. This is obviously how sort of this kind of first order differential equation. So divided by concentration of A, this is equal to K dt. So I'm going to introduce integration, but where am I going to pick limits? If I consider that at T is equal to 0, the concentration is equal to this, and then at after time T, okay, the concentration is going to be concentration of A. That is what we are going to consider here. So meaning we're going to integrate from concentration at T is equal to 0 up to concentration at T, okay, negative dA, okay, is equivalent, we are integrating from 0 to T and K dt. So if we do the integration here, what does this give us? This is going to give us what? This is going to be, remember this is out of the concentration of A. So this gives us natural logarithm, okay? The natural logarithm of concentration of A, okay? And we are to substitute in the limits. So we have limits like this. And this is going to give us KT. Okay, so let's substitute in and we see. This is going to be negative natural logarithm of A T, then plus natural logarithm of A, concentration of A at T is equal to 0. And this is giving us what? This is going to give us KT. So finally, what does this give us? This is a natural logarithm of the initial concentration of A minus natural logarithm of the concentration at T is equal to T, or after time T. This is equal to KT. So what does this mean in logarithms? First of all, this is going to mean natural logarithm of A at T is equal to 0 divided by A at after time T, and this is giving us KT. So now let's see Remember, this represents logarithm to base e of a at t is equal to 0 divided by a after t, concentration of a after t. So this is giving us kt. So if we convert this to logarithm to base 10, this is going to give us logarithm to base 10 of e, okay, and yes, this is of concentration of a at t is equal to 0 divided by concentration after t. Then we are dividing it by logarithm, okay. This is, remember we said this, if we take both sides, we take logarithm to base 10 here, this is going to be this, and divided by, this is going to be what? So let's first see. So this is going to be, divided by log e to base 10. And so if I take logarithm of e, okay, so first of all, I go to my calculator, press alpha, and get that e. I press equals, I get the value. So I take log of that answer, and I'll have 0.43. So if I have 1 divided by that answer, I'll have the value. Remember, this is equal to kt, and this is going to be 2.303 logarithm to base 10 of concentration of A at t is equal to 0 divided by concentration of A after t, time is equal to t seconds. And this is equal to kt. So finally, if we are looking for the equation to determine, for example, any of these, if you're given time, you know the initial concentration, that means you can get the concentration at any time t. So ladies and gentlemen, what we are going to do now is the half-life for first order. So half-life here is going to be what? We are going to modify now our equation and say that after t is equal to t a half, then this t a half will always equal to the initial concentration divided by 2. So I'm going to substitute in this equation, and this is what I'm going to have. I have 2.303 logarithm of concentration of A at t is equal to 0 divided by concentration of A at t is equal to 0 divided by 2. So this is going to give us kt a half. So we are on the journey to get this value, and this obviously will give us 2.303, okay, logarithm of 2, yes, and this is going to be kt a half. So let's see, 2.303 times logarithm to base logarithm of 2 to base 10. This gives us 0.693 equivalent to k t a half. So that's why t a half, that is the half-life for first order reactions, is equal to 0.693 divided by k. So that's why we have that expression here. So that's where it comes from. So in the next discussion, we are going to be looking at second order reactions. Examples of first order reactions. So first of all, we know that all radioactive decays are what? Are first order reaction. Then two, another example is the decomposition of hydrogen peroxide to form water and oxygen. So decomposition of hydrogen peroxide to form oxygen and water. So this reaction obviously takes place under the presence of a catalyst that we call the manganese 4 oxide. So the reaction proceeds as follows. So you could have manganese 4 oxide, this is a catalyst, and you're forming water and oxygen gas. So if we are to balance, we could put a 2 here and put a 2 here. Then the next equation or the next example would be, the next example is going to be the reaction of 2-chloro-2-methylpropane with sodium hydroxide. So reaction of 2-chloro-2-methylpropane with sodium hydroxide. So this is going to react with the sodium hydroxide, and this is going to form. So we have the 2-chloro-2-methyl. This is CH3. Okay, this is 3Cl. In the presence of sodium hydroxide, we are going to get CH3, 3COH, then plus a chloride ion. Then the other example is going to be the decomposition of dinitrogen pentoxide to nitrogen dioxide and oxygen. So we have decomposition of dinitrogen pentoxide. We are forming to nitrogen dioxide and oxygen. So the equation for the reaction is going to be N2O5, and this is giving us nitrogen dioxide gas plus oxygen gas. So we can put the 2 here, this becomes 10, and we can put the 5 here. So those are the applications for those are the examples for first order reaction.